The next special case we're going to look at is where both materials are perfect dielectrics. So the conductivity of material 1 and material 2 is 0. So we do not have an attenuation constant, and the intrinsic impedances in the two materials are both real numbers. Some of our incident wave will be transmitted because now our transmission coefficient will be non-zero. Again, the electric field intensity in material 1 will be the sum of the incident and reflected waves, and for the amplitude of the reflected wave, we will substitute the reflection coefficient times the amplitude of the incident wave. Let's add and subtract this same quantity now from our expression for our electric field intensity in material 1. Let's rewrite these first two terms and these last two terms in the following way. If we multiply this by e to the j omega t and take the real part, we see that this first term is a propagating wave and this second term is a standing wave. This should agree with the mental representation you have. You know that part of the incident wave transmits into material 2. So this first term is the part of the incident wave that is going to transmit into material 2. This second term is the resulting standing wave from the part of the incident wave that does not get transmitted into material 2 and the reflected wave. To help visualize this, go to YouTube and search for standing wave pattern animation, and you'll see this video come up. The blue wave is the incident wave propagating in the plus z direction, and the red wave is the reflected wave propagating in the minus z direction. The sum of the incident and reflected waves is this black wave, so the black wave represents the electric field intensity in material 1. And of course, this is the transmitted wave. The incident wave is creating the reflected and the transmitted waves. So the transmitted and reflected waves will oscillate with the same frequency as the incident wave. The velocity of the electromagnetic wave is 1 over the square root of mu epsilon. Since the two materials will have different dielectric constants, the velocity of the electromagnetic wave will be different in material 1 and material 2. But we know that the frequencies are the same, so that means the wavelength of the electromagnetic waves will be different in material 2 and material 1. Of course, the incident and reflected waves, which travel at the same velocity, have the same wavelength. Depicted in the bottom half here is the total electric field intensity in material 1 and material 2. As you run the animation, the total electric field intensities in material 1 and 2 will accumulate. So essentially taking a picture every delta t and superimposing all those pictures in the bottom part of the figure here. This would be the situation after the animation has run for a while and you've taken about a dozen such snapshots. So in material 2, this would be about the distance that the wave will have propagated. Now let's look at the situation after a long time has passed. So at a given location in material 2, the electric field intensity will be moving up and down between plus 0.5 and minus 0.5 at any particular point you look at. In material 1, the amplitude of that oscillation will vary with position. So for instance, at this point, the electric field intensity will oscillate between 1.5 and minus 1.5. At this point, between 0.5, and minus 0.5. So go to any location, and this dot signifies what the electric field intensity oscillation will be. This pattern in material 1 is a consequence of having both a propagating wave and a standing wave in material 1. Let's go ahead and run the animation. So these values right here are the maximum amplitude of oscillation of the magnetic field intensity in material 1. And these points here are the minimum of amplitude of the oscillation of the electric field intensity at any location in material 1. So for this example, Emax is 1.5 and Emin is 0.5. The standing wave ratio, or SWR, is defined as this max over this min. So for this example, the standing wave ratio is 3. If you think back to our previous example, where material 2 was a perfect conductor, so there was no transmission, everything was reflected, the E minimums were 0. So in that case, the standing wave ratio would be infinite. If material 2 had the same dielectric constant as material 1, you'd have the same intrinsic impedances in your two materials, so your reflection coefficient would be 0 and your transmission coefficient would be 1. So the incident wave would just continue propagating into material 2, and you would have no reflection, so you would have no standing wave pattern. And so your minimum and maximums would be the same, and in that case, your standing wave ratio would be 1. So your standing wave ratio will vary from 1 to infinity, 1 when you have total transmission, and up to infinity when you have total reflection. Let's go back to this form where we have our incident wave and our reflected wave, and let's factor out our incident wave from the first and second terms to get this form for our electric field intensity in material 1. So if we multiply this by e to the j omega t and incorporate that j omega t in this first term and move it over here, this is the form for our electric field intensity in material 1. So you see we have a propagating wave with our amplitude that varies with position. That variation in amplitude with position is what we saw here in this animation. The variation in amplitude is given by this exponential term, and so since gamma can be plus or minus, the maximum value of the amplitude is e sub I 0 times 1 plus the absolute value of gamma, and the minimum value of the amplitude with position is e sub I 0 times 1 minus the magnitude of gamma. So the standing wave ratio, the ratio of E max to E min, is 1 plus the magnitude of the reflection coefficient over 1 minus the magnitude of the reflection coefficient. We are going to look at two cases. The first case is when the dielectric constant of material 1 is greater than the dielectric constant of material 2. So the intrinsic impedance of material 2 is greater than the intrinsic impedance of material 1, and the reflection coefficient, therefore, is going to be positive. So the velocity of the electromagnetic wave in material 1 will be slower than the velocity of the electromagnetic wave in material 2. The frequencies will be the same in both materials because the oscillation is coming from the incident wave, and so the wavelength in material 1 will be less than the wavelength in material 2. This is the situation when the dielectric constant of material 1 is greater than that of material 2. So the wavelength in material 1 is less than the wavelength in material 2, and your reflection coefficient is positive. So here's the incident wave, here is the reflected wave. Down here we have the corresponding standing wave pattern. In the second case, the dielectric constant of material 1 will be less than the dielectric constant of material 2, so the intrinsic impedance in material 2 will be less than the intrinsic impedance in material 1, and so with eta sub 2 less than eta sub 1, the reflection coefficient is going to be negative. The velocity of the electromagnetic wave in material 1 will be greater than the velocity of the electromagnetic wave in material 2, which will mean the wavelength of the electromagnetic wave in material 1 will be greater than the wavelength of the electromagnetic wave in material 2. And that case is shown here where the reflection coefficient is negative, so here's the incident wave, here's the reflected wave, and the wavelength in material 1 is greater than the wavelength in material 2. Here we have the corresponding standing wave